Pleasure today to introduce my longtime friend and colleague, Mike Garcia from the University of Hawaii. Mike received his PhD many decades ago from University of California. You had to say that yesterday. At University of California at Los Angeles, UCLA. He immediately took a position at the University of Hawaii and has been there ever since. He has had visiting professorships around the world at Japan, Australia, including Macquarie and the ANU, at the Philippines and at MIT. He collaborates widely, and in particular, he has particular skills at linking volcanology, metrology, geochemistry, and as you'll see today, geophysics. He's a fellow of the American Geophysical Union and the Geological Society of America, and today he's going to tell us about the world's largest and hottest shield volcano, Pūhāhonu. Thank you, Mike.
Aloha, everyone. Thank you. It's a pleasure to be here and to join you once again. I wish I was in Canberra instead of in Honolulu, but maybe at some future date. So first I want to acknowledge my co-conspirators in this investigation, Jonathan Tree, who did most of the mathematical modeling on the petrology and geochemistry, Paul Wessel, who did the modeling of the volume sizes, and John Smith, who was involved in compiling the maps that I'll show you today. So I couldn't have done this study without those three gentlemen. Also, I want to mention that the name of this volcano is a new one that the Hawaiians gave to this landmass. It's called Pūhāhonu, which is Hawaiian for turtle rising for breath, which is the reason for that photo you're seeing, is a turtle is coming up for breath. Okay, in accordance with your tradition, I want to acknowledge the land here. This is indigenous space, which was originally identified as the people were identified as Native Hawaiians. The Aina, or the land in which I've been privileged to live and work for 45 years, is located in the Apua'a of Waikiki. I recognize that Her Majesty Queen Iliuokalani yielded the Hawaiian Kingdom under duress and protest to the United States to avoid bloodshed of her people. I further recognize that generations of indigenous Hawaiians and their knowledge shaped Hawaii in a sustainable way that allows me to enjoy her gifts today. For this, I'm truly grateful. All right, a brief outline for this talk. So what we're doing here is actually rediscovering a comment that was made back in 1974 by Jackson and Wright, by Bargar and Jackson, that this volcano is actually the largest one in the Hawaiian chain. But what we've done is do new volume calculations as well as modeling the temperature from whole rock compositions to try and update the story. The implications for this work suggest that the Hawaiian plume magma flux has been highly variable, unlike many other plumes, which have shown a more or less progressive decrease with time, such as the Louisville chain. Now, I would emphasize to all the younger people here that there's still many discoveries to be made of the Earth's submarine world, and this volcano is just one of them, the story I'll tell today. As Dick Archelaus mentioned earlier, this work was originally published a year ago in Earth and Planetary Science Letters, and I encourage anyone who would like to know more about what I'll be speaking about today to peruse that paper, which has many more details than I'm able to share today. All right, so Mark asked me to mention a little bit about what motivated us to do this study. And I would emphasize the concept of serendipity. We had no intention of pursuing this project originally. What had happened was the former CEO of Google, Eric Schmidt, and his wife, Wendy, set up a new marine program in which they had a ship built and commissioned, and they were looking for some projects to do, and they decided to work on the newly expanded Hawaiian Marine Natural Monument. So they put out a call of people who might be interested in working on this project, and so I volunteered my class of grad students to work on it, and we went out and got funding from the National Science Foundation of the US to put a gravimeter on board the ship to complement the bathymetric studies that were being done. And so this study I'm talking about today is just a small part of that overall larger project. All right, I'm sure most of you are familiar with where the main Hawaiian islands are. Voon was talking about the island of Hawaii, where she's done a lot of work on Kilauea. I'm located on the smaller island of Oahu, and there an arrow and a red asterisk shows the location of the university. Now, the islands are part of the Hawaiian Emperor chain, which is shown there in the lower left, which consists of the older Emperor seamounts, and there's a bend in the chain. And then you have the Hawaiian Ridge, which is broken up into two segments, the Northwest Hawaiian Ridge and the Hawaiian Islands. The red circle shows where Puu Honu is located. Now, this is what Puu Honu looks like now. It's basically a remnant of the once majestic volcano. It's two small islands covered in bird guano that exist today. The islands were first reported to have been sighted back in 1820 by an American whaler, but these were known to the Hawaiians who traveled up the chain for many generations. The first recorded landing was by an actual Russian vessel back in 1828. President Roosevelt, back in 1909, included this island as part of the Hawaiian Islands Bird Reservation. And as you can see, if you look closely, there are birds surrounding and flying all over this area where they come to the island to nest. Okay, reminder, the ocean floor around the Hawaiian Islands is 5 kilometers deep, 5 kilometers. So it's bloody deep. And in order to get an island, the volcano has to rise at least 5 kilometers above the seafloor. So here's a perspective look at the Hawaiian Islands. And if you look closely, you might be able to see the horizontal lines, which are 1 kilometer contours. And then the white star shows the location of the summit of Mauna Loa. So these are bloody big mountains. If we drew a cross section through Mauna Loa, or the island of Hawaii, you can see there are two peaks, one which has the arrow, which is Mauna Loa, and the one next to it on the left, which is Mauna Kea. These guys are actually quite a bit taller than you might expect because there is a keel underneath the volcano that extends down another 4 kilometers or so. So the overall mass is perhaps on the order of 13 kilometers, which is certainly much larger than Mount Everest, which is built up on a high plateau. Just for perspective, if you include the local Australian mountain, you'll see it's many times the size of that little guy. All right, here's a map that was published back in 2013 that shows both the Northwest Hawaiian Islands and the main Hawaiian Islands. So the feature that used to be called Garden of Pinnacles and was renamed by the Hawaiians as Pūhāhonu was considered by Bargar and Jackson back in 1974 as the largest Hawaiian volcano. However, the Hawaiian Islands themselves were re-examined in 2006 as part of a study to include the flexural component of the total volcano mass. So you're looking at the keel of the volcano as well as that part which is above the seafloor. And in doing so, they found that Mauna Loa was considerably larger than the old Garner Pinnacles. Now, unfortunately, Bargar and Jackson had very little bathymetric data on which to base their estimate, and they had no knowledge of the keel of the volcano. So for another 10 years or more, this sat dormant in terms of everyone believes, and still, if you wish to consider it, Mauna Loa is the largest active shield volcano. All right, here's a map that was compiled by John Smith, in which he took the new data that we collected during 2 cruises on board the Schmidt Institute of Oceanography ship, as well as combining that with other pre-existing data in compilations that within the University of Hawaii, as well as had been published, to create this map. So the white outline shows the U.S. Marine National Monument, with the expanded boundaries that motivated the expedition by the Schmidt Institute. Okay, here's another map that John compiled just of Puu Honu. And what I'd emphasize here is the enormous size of this feature. We estimate it's at least 290 kilometers long and about 90 kilometers wide. And Mark pointed out to me, this is about 10 times the size of the Australian Capital Territory. So it's truly an enormous feature. So if we look at this feature, we could perhaps project onto it 3 rift zones, one going off towards the north, which is about 150 kilometers long, another one that bends off to the south, and then a third smaller one that goes off to the northwest. Now, when I presented this work at the 2019 AGU meeting in San Francisco, Dave Clegg took exception to this notion, and he said, well, there's actually 5 volcanoes. It's not 1, it's 5 volcanoes. And I said, gee, Dave, why do you say that? And he says, well, if you look at the coral reefs, you can see that there's many different volcanoes. I said, well, a better way to approach this problem is to look at the gravity signature. And the reason for that is that in the summit of the volcano, you have a magma chamber, and there you have denser minerals collecting that gives it a gravity high. And likewise, along the rift zones, you have dike intrusions, and when those crystallize, they form dense masses. So if we look for the gravity signature, then we should be able to recognize how many volcanoes are within this mass. So this next slide is another compilation by John Smith showing where we collected gravity and where gravity was available. So these wiggly lines show where the ship tracks were. The ship tracks were constrained based on time to be where we could maximize the depth coverage. So you're driving a ship along and it can look at a 10-kilometer swath underneath the ship. So we didn't want to survey the shallower parts of the volcano because the ship track would only be a few hundred meters, the bathymetry track would only be a few hundred meters wide. So instead, we concentrated on the deeper parts of the volcano. So that's where our gravity data are located. So I've emphasized looking at the colors. The red colors show the higher density areas, and the blue colors show the lower density areas. And what I hope you see is, for instance, this volcano we're calling West Pūhāhonu has a high density area. So that's clearly one volcano. And then we move to the west and you see move to the east, you see a separate volcano that we're inferring a well-developed dike zone moving off to the north, a poorly developed one to the south. And we infer that the summit area is where shown by the P is where the summit of the volcano is. So a simple reconstruction would say, perhaps there are 2 volcanoes, one on the east side and a much smaller one on the west. Okay, going back to the bathymetry map, what I want to emphasize to you, first, if you notice the contour lines, they're spaced every 200 meters. So you can see that the shallower parts of the volcanoes are quite low relief in terms of widely spaced contours. And we infer that to indicate that the volcano was actually subaerial at the time for a while, and that these areas were extensively eroded. And also as it was sinking, and all the Hawaiian volcanoes sink very rapidly during their growth and afterwards, that a carbonate bank built up on top of it, emphasizing or contributing to the overall relatively flat nature of the volcano. This cap over on Midway, which has been drilled, is on the order of 400 meters thick. So we assume that the cap here at Puu Honu is probably on the order of 400 meters thick. Now, in addition, if you look off to the lower left, you can see landslide debris. So those blocks were once part of Puu Honu that have broken off and slid off towards the west. This is a typical feature in Hawaiian volcanoes. Virtually all the volcanoes has landslided, in many cases multiple times. Another feature to notice is a slope break. This is an indication of where the horizontal rocks, which were cooled slowly, run into where the submarine rocks were cooled rapidly. So this nick point or slope break represents perhaps the old margin of the island at its maximum extent. This is work that Jim Moore pioneered back in 1987. So if you look closely, you can see this slope break and you can follow it along. It's shallower on the rift zones and deeper near the center of the volcano, which reflects perhaps the greater subsidence. Now, if we take that slope break and say, all right, that's the old shape of the island, we can then draw out what the Puu Honu coastline might have looked like at its maximum size. So you see the one volcano compared to the island of Hawaii, the big island, with its 5 main volcanoes, and you can see that it's comparable in size at that time. Now, this ignores the fact that the northern part of the Big Island has subsided already 1,000 meters. The volcano on the northeast side, Mauna Kea, has subsided 400 meters, and even Mauna Loa, which is still erupting, has subsided 150 meters. So the island was at one point, at variable times, much larger to the north and than we're showing in this current coastline. But anyway, the masses were similar in size. All right, so next we want to know something about the volume. So what we're doing here is we're showing a model that has been used by others to estimate the size of the Hawaiian volcanoes. And it takes a very conservative approach in doing so. We don't try to include the sediment, which undoubtedly is mostly derived from the volcano itself, but there's a big moat surrounding the islands of sediment that was primarily derived from the volcanoes. We don't include that, or the portions of the volcano that perhaps interfinger with that sediment. So that's excluded. We just take the seafloor and propagate it down and say, right, that's a conservative estimate of the size of the volcano. Now, the other part of this is that's not well constrained is how deep does the volcano subside into the underlying crust? And that's inferred to be on the order of, well, we're using the 450-degree isotherm, but Paul Wessel, who did this modeling, says, well, it's plus or minus 150 degrees. So that puts in a 20% uncertainty in his volume calculation. So this is the same basic method that was used by Robinson Eakin to look at the volumes of the Hawaiian volcanoes. So what do we get? Well, for Pūhāhonu, we get a volume around 150,000 cubic kilometers, plus or minus around 30. So a pretty substantial volume. Whereas Mauna Loa was estimated to be around 75,000 cubic kilometers. So roughly, Pūhāhonu is twice the size of Mauna Loa. Now, the estimates for Mauna Loa are kind of tricky because on the Big Island, you have the interfingering of the various volcanoes. So it's really not clear exactly how much to attribute to one volcano to the other. So Mauna Loa may actually be considerably larger or might be smaller, depending on how much overlap you allow with the volcanoes. But if we stick to the overall mass of the volcanoes, in this case, we consider the volume of West Pūhāhonu, and Pūhāhonu itself, and compare that to the island of Hawaii, the volumes are similar. They overlap within the uncertainty of the errors that Paul has estimated. So indeed, this was quite a substantial mass, this volcano. Now, you might be asking, well, why did this volcano complex get so big? So there are many different hypotheses you might consider. And some that are testable include a thin lithosphere. So if the lithosphere is thin, the theory is that the amount of partial melting will be greater as the magma or the plume rises to shallower levels, undergoes more extensive melting. But this was not the case for Pūhāhonu because the lithosphere was relatively old at the time it formed, around 80 million years, and so was relatively thick. Likewise, if the propagation rate was slow, perhaps it sat over the plume for a longer period of time, and therefore it could grow to a substantial mass. But the work of Jika et al., who I collaborated with on the study, shows that no, it was actually relatively fast, on the order of 87 kilometers per million years. So that's not an explanation. So the other potential source you might consider is, the source was more fertile, so it underwent a larger degree of partial melting. But that's not the case. The source is similar to the source of the surrounding volcanoes, what we call the Kea-type source. So it wasn't enriched. It shouldn't have produced more magma. So what are we left with? Well, there was an idea proposed back in 1903 by White, suggesting that, the plume was hotter. So we figured, right, we'll test this hypothesis using the methods that Paterka et al. Has developed over the last decade or two to evaluate that. So luckily, there's samples available from this complex. So back in the early 70s, Brent Dalrup and others went to the island and collected samples. And as you might guess, bird deposited rocks are not going to be very fresh, sitting out there for a long period of time. So those were not suitable. But there are 4 dredge hulls that return rocks, and they were pretty decent shape. So we chemically analyzed these, and they were reported in a paper in 2015, another one in 2018 by Harrison and Weiss. And these rocks are basically tholeitic, which is typical of the shield stage of volcanism, and weakly alkalic, which is typical of the post-shield stage, based on the trace element and isotopic signatures. And they're, as I mentioned earlier, Kea-like in composition. So we took the best of the best, 6 very weakly altered rocks that were olivine rich to work on. And these rocks come from the 1976 dredge hull, which is shown here in red. So these rocks were also previously dated by Brian Jika, and we got an age of around 14 million years. So we have a rough idea, well, we have an idea of when this volcano was active. Okay, here's a photomicrograph. Oh yeah, there's the scale. So that's a 0.5 millimeter scale on this photomicrograph taken in plain light. And here you can see the beautiful olivine crystals, and that dark thing there is a chromite grain in a fine grain matrix, and it's relatively non-vesicular. And these rocks are very olivine rich. We'd call them picrites, or very olivine rich rocks. The whole rock compositions are relatively magnesium rich, 12 to 17%. And they have magnesium numbers that are relatively high, 68 to 70, assuming an iron, ferrous iron component of 90%. So we analyzed a lot of olivines from 6 different samples, over 300 samples. And what we found is these olivines return relatively high forsterite contents, 89 to 91. And the highest one was actually the highest we've ever seen in any Hawaiian rock, a forsterite content of 91.85. Now those are values typical of mantle olivines. So your question is, are these really things that grew in the magma, crystals that grew in the magma, or are these artifacts that have been brought up in the magma? And we found these kinds of xenocrysts in other Hawaiian basalts. So we wanted to make sure these things were actually cognate or grew in the magma. Well, how do we do that? Well, we looked at the shape of the olivines, and you can see here they have a nice crystal shape to them. Also, this one crystal that had the highest forsterite content has a melt inclusion. So this would strongly suggest at one time in its history, there was a melt surrounding it, and that olivine continued to grow and encapsulate that melt, that early form melt. We also looked at the calcium content of the olivines, and they're relatively moderate, indicating crustal level crystallization, whereas a mantle olivine would have less than 1/10 of a weight % calcium. So we think these things all point towards a crustal origin for all of these olivines that have high forsterite contents. Now, as you all know, who probably, if you watch the videos from the 2018 eruption, that Hawaiian magmas are characterized by very fluid lavas. And indeed, these things are quite hot. But we wanted to be able to estimate the mantle potential temperatures, and we did so by using methods that Keith Peterka has pioneered. So we looked for the highest forsterite contents in these olivines. And using those olivines, we got the temperature of around 1700 degrees centigrade, plus or minus 56 degrees at a 2 sigma value. So this temperature is the hottest temperature, not only for any Hawaiian rock, but also for any Cenozoic basalt anywhere on Earth. So you might ask, so what made these magmas so hot? Well, one explanation that has been invoked elsewhere is solitary waves were responsible. So what's up with a solitary wave? How is this playing a role? So this numerical modeling cartoon was done by Dutta and Mandel back in 2017. And what I want to point out to you, these blobs, these red blobs within the plume structure that are the solitary waves as they move up through the conduit of the plume. So this was demonstrated and pioneered by Scott et al. Back in 1986, and then utilized by various studies which were looking at the volume variations along hotspot trails. And so this was done for Iceland by Garrett Ito, 2001, the Azores, and even for Hawaii by White back in 1993, and Van Ark and Lind back in 2004. So our petrologic results actually show that these are thermal pulses as well as perhaps greater masses. And the notion is that these solitary waves allow hotter magma to rise up within the plume and undergo perhaps greater extents of melting, which according to the methods we use at Peterka, might be as much as 24% partial melting. All right, if we step back and look at this temporal variation in the Hawaiian plume output that Paul Wessel has shown back in 2016, you can see that Puu Honu is one of the largest outputs along the chain, except for the island Hawaii. Then the big island Hawaii, and then another one I'll draw your attention to here is Midway. So there has perhaps been a pulsing of the Hawaiian plume. Large pulse here for the island of Hawaii, somewhat smaller one for Puu Honu, and then a much smaller one for Midway. So it would appear that unlike other plumes that seem to show a history of progressive decline, the Hawaiian plume has undergone a series of surges in its history. And if you go back to the area over here where the bend has occurred, the output of the Hawaiian plume was fairly low after the bend. It went up as we had the Midway complex, went down again, and then rose during the development of the middle part of the Northwest Hawaiian Ridge. It descended again just before the island of Kauai, and then has undergone a rapid increase. Okay, there's a diagram that Jonathan Tree had in his master's thesis showing the other samples that he looked at as part of his study. And yes, the Gardner or Puu Honu is the hottest one, around 1700 degrees. And this compares favorably with the work that Keith Peterka did on Mauna Loa. Now, the other volcanoes along the chain seem to show a more or less good correlation with the volume that's been estimated by Paul along the chain and the temperatures have inferred from the olivines and the whole rock compositions that we estimated. So there's a consistent story here in terms of correlation between the inferred volumes along the chain and the temperatures that we calculated from the olivine whole rock compositions. Now, another way to look at this volume output is to look at the swell heights. And this was done by Paul back in 2016. And this is an adaptation of his earlier study. And you can see in dashed lines here, the trace of the Hawaiian chain. So here's Midway over here, Puu Honu, and then the island of Hawaii is shown there. So indeed, there has been a significant pulsing of the Hawaiian chain over the last 25 million years or so. Okay, so in summary, Pūhō is perhaps the largest shield volcano of Earth, at least within the last 65 million years, and it's perhaps twice the size of Mauna Loa. We think it was big because the olivines indicate to us that the temperatures were high rather than the source was fertile. What caused it to be so hot? Perhaps a solitary wave is the reason for the pulsating of the Hawaiian plume, particularly for the Puu Honu area. And I want to emphasize that we continue to learn new things about the Hawaiian emperor chain, which is, I think most people would agree, the best sampled and best analyzed chain in the Hawaiian Islands, or on the Earth. And we continue to learn new things about the mechanics and thermal evolution of the Hawaiian plume. So one thing I'd also like to mention is we have a new suite of samples that were collected from the empress seamounts, and we hope to pursue with future funding, look at the empress seamounts and see what insights they provide for the overall Hawaiian chain. And then I want to emphasize, acknowledge the contributions, not only from the Schmidt Ocean Institute and providing us access to the ship and surveying the Hawaiian, Northwest Hawaiian chain, but also the people on board the ship that ran the ship and the scientists, including the grad students from the University of Hawaii that were involved, as well as grants from the U.S. Science Foundation to both myself, Garrett Ito, and John Smith. And with that, I'll open the floor to questions.
Thanks, Mike. If anyone wants to ask a question, feel free to raise your hand or unmute your mic and start asking.
Yeah, I've got a question or two.
Oh, well, of course you do.
Yes, absolutely, Mike. Hey, wonderful stuff. My question is, how did you, and they're in the appendix, the table, how did you calculate the parental melt or the melt compositions for the different samples you have?
Well, thank you for asking, Richard. If we go back to the talk, Mike, and the one thing about Jonathan, he was very mathematically inclined. So he did Monte Carlo simulations, and he did up to 1 million separate calculations, assuming different KD values for the olivine and the magma. So this shows a summary of that. And then here's the equation from the Petrarca paper, in which he did the calculations to infer the olivine liquid composition. So that's summarized there, which includes components of the major composition of rocks. So Jonathan did 1 million different possible simulations in doing this. And then for the pressure estimates that we needed to utilize in doing the iterative calculations, he used this equation from the Petrarca 2008 paper. And then lastly, no, it's not lastly. This then allows him to calculate the potential, metal potential temperature for these things, which also requires an estimate of the amount of melting, the F, and that's given in this equation from the Petrarca 2016 paper.
Yeah, okay.
There are people who want to dig into these things because they're not in the paper.
Yeah, so having done that, did you have any data for, was it a single melt inclusion that you guys had in that most specific olivine?
We did not analyze that because that particular melt inclusion and all of the melt inclusions had undergone significant crystallization.
Yeah.
So you have to really pair into that to look at the amount of post-entrapment crystallization to back calculate the composition. So we just went with the whole rock composition and then used Danshevsky's program to back calculate the parental magma composition.
Okay, one final comment or question to you. Did you analyze the chrome spinels? The spinels, sorry, I said they're chrome, but are they chrome?
Well, they're very strongly chrome spinels, and some of them are actually translucent. So yes, we have done that. And we thought about using the chrome spinel olivine geothermometer, but in the end, we didn't trust that as much as we did the Paterka method.
I think that's worth doing, Mike. It'd be more convincing if there was some agreement. I mean, I'm a fan of Keith Paterka and the stuff, but it's like, hang on a moment. It's worth checking other independent mineralogical, petrological tests.
Okay. So I have some data. I didn't do a lot of studies of the chromites, but yes.
Very good. Well, anyway, thanks. Fascinating studies. Congratulations.
Well, I'm hoping that this group, or perhaps afterwards, will have comments like yours to pick holes at this kind of work to see where the weak links are and see if we can refine this to get a better understanding.
Hello.
Mike, it's Greg. How are you?
Whoa, Greg Yaxley, the distant past.
So the mantle potential temperature that you've come up with is extraordinarily high. Why aren't these things komatiites?
Well, I would assume, Greg, that they underwent significant crystallization during their transport upwards. That much of the olivine cargo has been lost as it was being transported from the plume up to the surface. These temperatures are not unduly large or unduly high compared to the ones Keith calculated for Mauna Loa. He got temperatures around 1650. So they're not a lot higher, and within the air, they're similar.
Yeah. Okay. Thanks.
That's the point. And certainly some of these, that temperature is certainly hotter than some of the komatiitic temperatures that have been calculated.
Mm.
Now, I assume the komatiites were wetter than some of these Hawaiian basalts, which I think are relatively water poor compared to some of the komatiites.
Right, so you do have estimates of the volatile contents of the
Yes.
primitive Hawaiian melts.
Yes.
Yep. And how does the Paterka thing cope with the iron 3 effects?
I just made an assumption.
Okay.
And this is based on a lot of work done by various studies, and it continues to be a moving target. Many people have been pushing for a 10% oxidized iron. Some people have pushed it back to 15%, but it's somewhere in that range. Likewise, the KD has drifted for olivine liquid for iron magnesium, has drifted from 0.30 to 0.345. So we experimented with 3 different compositions and found the one that explained the data best.
Yep. Cool, thanks.
Audrey, you're next.
Cool. Hi, Mike. Thanks for the talk. I just have a question on the dynamics. So you've invoked potentially this soliton mechanism where you have thermal pulses in the plume. Sorry, can you hear me?
Yeah, no, I'm just trying to hide. You're going to ask me a geophysics question.
No. It's so obviously when you have a larger thermal pulse, you have a larger thermal buoyancy. So I would expect that thermal buoyancy can overcome potentially some of the negative chemical buoyancy from the deep mantle. So you potentially expect that when you have those positive pulses in temperature, you'd expect a compositional change associated with that because it can bring up essentially more of the dense material.
Yeah.
So I'm wondering if, so you hinted that I think it was K in composition, but do you see anything relative to the volcanoes either side that suggest nothing at all?
So that was well documented in the papers by Harrison and Weiss, that they look more or less the same. There's nothing anomalous. But perhaps the Sarah Lambert study where you look at the first row transition elements might show us something that we didn't really look at very carefully.
Okay.
We looked at things like rare earths and other highly incompatible elements to see whether there was some signature there, and there wasn't.
Okay, thank you.
I guess can I ask a question? So,
No.
so for the pulsing history, how far back can you go? Like, can you go beyond Midway and along the entire Emperor Seamount chain? Oh.
I'm sorry, you're asking which?
So to identify sort of the pulsing history of the thermal plume.
Well,
can you go?
all the way to the trench, the Kamtanka Trench. So yes, we can do all the emperors. And in fact, that's the next component of the work we'd like to do, is to extend the study up the chain. So we've gone, that slide I showed you from Jonathan Tree's thesis had a seamount right south of the bend. So we've gone all the way just before the bend.
Yeah.
And there's the sampling gap right at the bend, but we have samples now all the way up the chain. And they were in fact samples drilled by the Ocean Drilling Program, more than 40 years ago, right next to the trench, Detroit Seamount and Meiji Seamount in the northern end of the Emperor chain. So we hope to include all of those, or at least some of these, along the Emperor Seamounts.
Okay. Thanks.
That was ODP leg 145, I think.
Well, it's before that. It was actually leg 19.
19.
Right, was 145. Were you on that leg, Richard?
No, but I got the ashes from it.
Oh, the ashes.
The ashes were coming off Kamchatka.
Ah.
Anyway, no. Fair enough. Leg 19. Are they decent samples from leg 19?
Well, you know, the surprising thing, Richard, is you wouldn't think they were. But when we went back and started looking into the collection, we got photographs from the ODP station in Texas, and they showed that samples were actually quite decent looking. So we've gotten samples from that collection, and yeah, they're pretty decent. And this was said by the original petrologic work that was done, but it's been largely ignored because some geochemists came along and said, oh, those are altered rocks. So everybody lost interest. So we went back, started looking in detail and said, hey, these are workable.
Yeah, very good. Best, all strength to your elbow. Keep going.
All right, I don't see any hands up, so I think we'll just end the formal part of Q&A. People are welcome to stay online and have informal discussion. And with that, let us thank Mike again for your fantastic talk today.
Thank you. Mahalo.
Hello.